This video covers the concept of heteroskedasticity in regression. Heteroskedasticity is a violation of Gauss-Markov assumption number 5. For ordinary least squares to be blue, we need to have all of those assumptions hold. Assumption 5 tells us that we should have what's called homoskedasticity, meaning the variance of the error term is some constant number across all the values of our x. If there is a violation of the Gauss-Markov assumption, it means that we have a non-constant variance. In other words, the variance changes as we move across x. As we see, the variance of the error terms is dependent on the value that we're looking at. Now we can have pure heteroskedasticity or impure heteroskedasticity. Impure heteroskedasticity is usually caused by specification bias, meaning we need to add a variable or fix our functional form or something like that. These pictures offer us a glimpse at homoskedasticity and heteroskedasticity. So you'll notice as you're going across the values of x here, that the distance that these dots are away from the line is approximately the same. In other words, if I were drawing bell curves over top of these, each of the bell curves would have about the same standard deviation. But if you notice panels B, C, and D, each of these shows heteroskedasticity. We see that the data points are quite close to the line here, and then as we move out on our x, the values of y tend to move further and further from the regression line. The error terms have different variations. If we were drawing normal curves over top of this, we would have a nice tight normal curve with a fairly small standard deviation. And here we would have a much larger, more spread out normal curve with a much larger standard deviation. This is the opposite case, where when we have a small situation or a small value of x, we have more spread in the data, but then as x gets larger and larger, we have less spread in the data. So we see this kind of motion here. This I always call the bow tie in panel D. We have a lot of variation early on, and then not very much variation, and then we have more variation again in our error terms. All of these things, panels B, C, and D, represent examples of heteroskedasticity, and this heteroskedasticity can cause lots of problems for us. So what are the consequences of heteroskedasticity? If you just happen to have pure heteroskedasticity, it does not cause the beta hats to be biased. But if you have impure heteroskedasticity, and that's due to an omitted variable, that could mean your beta hats are biased. They could be too large or too small, depending on the omitted variable and its correlation with the included x variable and the y variable itself. One thing we do know about heteroskedasticity, if we have it, our standard errors of our betas are not correct. They can be overestimated or underestimated, which makes it really difficult to know and trust what our t-scores are, and in turn what our p-values are, and so it affects our chance of committing a type 1 and type 2 error, and it also affects the adjusted r-squared. We do not know if those standard errors are overestimated or underestimated. So this actually creates a lot of uncertainty in the robustness of our hypothesis tests. If the standard error is overestimated, that means that our t-scores will be extra small, which will mean we'll have an increased chance of committing a type 2 error. If our standard error is underestimated, our t-scores are too big, and that will increase our chance of committing a type 1 error. We never know which of the two scenarios we've actually encountered on the front end of this. How do we detect if we have heteroskedasticity? There are 3 things we're going to use to detect heteroskedasticity. The first is graphing each independent variable versus the dependent variable. We want to look to see if there's some kind of pattern like we saw above in our data. Also, when we run regression, we can ask the computer to spit out a residuals versus fits graph, and we'll look for a pattern in that graph. The same kind of thing we looked for above. And then we're also going to run something called the white test. What the white test does is allow us to see if the x's explain the residuals. So we run the regression for y as a function of our x variables. So I wrote this out just assuming we had two x variables to keep this really easy. Y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus our error term. When you run this regression, you're going to store the residuals. This is quite easy to do in Minitab, and I'll show you how to do this in a moment. We then calculate the residual squared. For each x, we calculate the squared term of x, and then we calculate each interaction term. So in this case, we only have two x variables, which means there's only one interaction term. How many interaction terms you have is k choose 2. Run the regression with the squared residual as your y variable. You want to keep each of the x's in there, and also the x squareds and the interaction term. The only thing we really need from this regression is r squared. Not adjusted r squared, r squared. So we're going to record the r squared from this regression, and we're going to use it to calculate a W score. The W score is that r squared times n. R squared is that unadjusted r squared, and n is the sample size. And then we're going to compare that to a critical value that we get from table B8 in the book. The test that we will run assumes no heteroskedasticity. In other words, it assumes homoskedasticity until we can prove that there is heteroskedasticity. In other words, if we're able to reject the null, we can say we have sufficient evidence to say there is heteroskedasticity. The decision rule will work just like most other decision rules. If our score is greater than our critical value, we reject the null. If our score is less than the critical value, we fail to reject the null. So we're going to use this example on petroleum consumption. This would be the demand for petroleum, and we're going to assume that that's a function of price per gallon and car registrations. The data we have is state-by-state data, and we're going to see if the price per gallon and the number of cars registered seems to determine how much petroleum is consumed. We're going to go over to Minitab so I can show you how to do each of these steps. So I'm going to open our Excel spreadsheet into Minitab. So this is quite easy to do. We've got headers in the first row. We just go ahead and leave that. Import rows 1 to 51. We have 50 states, so we want to let it import all of this data. Hit OK. So our data is now imported into Minitab. Once we've imported our data into Minitab, the first thing we're going to do is create our scatter plots. So we're going to go to Scatter, and then I always like to pick the one with the regression line. This just gives me a better eyeball of the dots and the distance that those individual data points are from the line. So I'm going to click into that till I get that black highlight and hit OK. Creating a bunch of scatter plots at once in Minitab is quite convenient. If we double-click our y variable in first, and then double-click one of the x's in, it will automatically continue to just move to the next box. Double-click the y again, double-click the other x. That's all we need to do for the scatter plots. So punch in our y variable, punch in our x variables, and we're going to get the two scatter plots. If we look at our first scatter plot, there does seem to be some potential for some heteroskedasticity. Most of the dots are pretty close to the line, but we have a couple of points, like this one and this one, that are far from the line. So let's look at the other scatter plot. Here is the scatter plot of consumption based on registrations. So how do car registrations impact the consumption of petroleum? This one looks even more heteroskedastic. With low numbers of registrations, the dots are very close to the line, and in places where there are high numbers of registration, the dots seem to move further and further away from the line. So now we're going to run our regression. We'll go to Stat, Regression, Regression, Fit Regression Model. We want to generate the regression for price and registration as it impacts petroleum consumption. So we'll double-click our petroleum consumption into the response variable, and in our continuous predictors, we have price and registrations. We want to go to the storage box now because we want to get the computer to store the residuals for us. So in the storage box, we're going to check this box that's called residuals. Hit OK. And before you leave this, go into Graphs, and you want to check the box that's residuals versus fits. You might recall we used residuals versus order for serial correlation. Now we're going to use residuals versus fits to try to see heteroskedasticity. Hit OK. Now we can hit OK again and generate our regression output. So we have our regression output here. For right now, we really just want to look at the graph and then move forward to our white test. So here's the graph of the residuals. We see a similar effect that we saw in that previous graph, where the dots are relatively close to the regression line for lower values and further away from the regression line for higher values. So we're pretty sure just based on these few pictures that we have heteroskedasticity. But we want to be truly sure. So no matter what our data, we're going to run the white test. Now we know we're more likely to have heteroskedasticity in cross-sectional data, but even if I had time series data, I would run this anyway. So let's hit OK and look at our stored residuals. To run our regression for the white test, we're going to use the square of the residual as our y. I'm going to let Minitab do the calculation for me. So up at the top here in Calculator, I can actually ask Minitab to generate a column for me of new values based on previous information in the data sheet. We're going to store the result in variable name what. I usually use something like residual squared so that I remember what this variable actually is. In the expression, that's where you put in your equation. So we want to square the residual. So double-click residual, RESI, caret 2. That's going to take each row of the residual and square it and store it in this new variable residual squared. So hit OK, and you'll see that new column come up. You notice here's the residual, and here's the residual squared. Those numbers look right to me, so I feel like we've probably done the right thing there. Okay, continuing on with the white test, we're going to go back to regression. Stat, regression, 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 fit regression model really. Hit OK, or click on that. We're going to replace petroleum consumption with residual squared. That's going to be our new Y variable. We need to leave in price and registrations. And then in the model box, we're going to generate those other variables that we need to have. We need to have each variable squared, and we need to have the interaction between each variable. So to make this easy, if we just hit Control and highlight the other variable, or you could highlight your range of variables, Control-Shift, and you can highlight your range of variables, we can actually very quickly add all the interactions necessary and all the squareds necessary. Now we only have 2 x's here, so we could do that pretty easily without this. But if I had 10 or 15 variables, this could be really, really efficient. So you see the 2 boxes here, interaction through order 2 and add. What that's going to do is take each of our x's and multiply it by each of the other x's in pairs. So for us, that's only going to be 1 pair here, but we'll go ahead and click add. You see the new variable added, price times registration. We're also going to go and click on this thing next to terms through order 2. What that's going to do is square each x variable and add it as a variable to the equation. Again, easy to do if we only had 2 variables, but if we had a lot of variables, this could do this very quickly for us. So we're going to hit add on this also. You see price times price, registration times registration. So it included now all the variables that we need. When we hit OK, you won't see those variables listed here, but they will be generated in our model. I'm going to uncheck a couple of boxes right now because I don't want it to store the new set of residuals that are going to be generated, and I also don't want to see this residual versus fits graph for my white test model. So I want to uncheck that stuff just not to clutter up my output. So now we're going to hit OK, and we'll get our new regression model. You will see that the Y variable is residual squared. Our X variables are price, registrations, price times price, registration times registration, and price times registration. So all the variables are in there that are supposed to be in there for the white test. Remember, the only thing I need from this test is the unadjusted R squared. The unadjusted R-squared is 84.97%. So let's remember that, and we'll go back to do the work by hand. So in Minitab, we generated our regression for white test. We got an R-squared of 84.97. We treat that as a decimal, 0.8497. And our sample size was 50. We had 50 states. So we do 0.8497 times 50, and we get a W score of 42.5. Now, that sounds big, but we don't really know much yet about what the critical value is going to look like unless you're peeking ahead here at what I've already written down. We use the chi-squared distribution for our W critical value for the white test. The chi-squared distribution I've shown here on the right just so you can get a sense of what that distribution looks like. It kind of looks like the F distribution initially and then starts to look more like a normal distribution for those of you that are aware of different kinds of distributions. To get the value that we need to come up with that 11.7 I've put here in our document, we need to look at the chi-squared table. For our model, we now have 5 variables. The 2 initial x's, the 2 squareds, and the 1 interaction term. That means we have k equals 5 variables in our equation. So 5 is our number of degrees of freedom. We're going to use the 5% level of significance, so that means our critical value is 11.07. 5 degrees of freedom would give us this tallest distribution. 11.07 would be a cutoff right here. So this is our critical value. Our W score is so far out to the right that it's beyond the axes that I've got here on my paper. So we can definitely say that we can reject the null. In other words, our model has heteroskedasticity. This is not really a big surprise because we have cross-sectional data and we have state-by-state data. Often state-level data will exhibit heteroskedasticity. Small states may have a different effect than big states. Now, if we have heteroskedasticity, what are the remedies? Often, we can fix heteroskedasticity by checking our specification. So it may be the case that we've left out an important X variable. Or we should have a different functional form. If that's the cause of our heteroskedasticity, we should fix that. It may also be the case that we need to calculate a weighted or transformed variable. So for the case that we're looking at, we might actually take the number of registrations and divide it by population. That may actually help us get at the root of our heteroskedasticity. How many registrations are there per person? If we do that, I suppose we should probably divide the petroleum consumption by the number of people also. So how much fuel is consumed per person, and how many cars do we have per person? That may help us get rid of our heteroskedasticity. If you calculate a weight or transform a variable and run a new regression, you could get rid of your heteroskedasticity. This should not change your betas. We want to be careful to know that we cannot compare the new adjusted R-squared to the old adjusted R-squared when we do this kind of weight or transformation. This should fix our standard errors so that we have more accurate results for hypothesis testing. There is something else that a lot of software can do that Minitab or Excel do not seem capable of, and that's adjusting the standard errors for heteroskedasticity. This can be done even if we can't fix the heteroskedasticity in some computer programs. Thank you for watching, and I'll see you again soon.